Chapter 2. Newton, Leibniz, and D'Alembert. Mathematical descriptions of physics must attempt to justify why their description should be a certain way or evolve a certain way, amongst all of the mathematically expressible possibilities. The answer, especially in the aftermath of the philosophy espoused by Maupertus and Leibniz, is typically some form of optimum selected on the state or the path of the motion, shortest path, for example. Given the idea of seeking a variational extremum, it then makes sense that there would be the invention or discovery of variational calculus. Prior to 1660, pre-calculus physics had acquired a body of observational data but did not have the mathematics invented yet to contend with describing trajectories and extremal paths, which those trajectories will be shown to be. That's not to say that a body of critical mathematics development hadn't already occurred, going as far back as the invention of primitive trigonometry with the concept of the sign of the angle sign was used in star tracking by Indian astronomers Gupta period, but the use of the method could trace back to the ancient Babylonians with future discoveries. Newton's fluxional calculus was invented in 1665 to 1666, during the London Plague, but he avoided direct use of infinitesimals in expressing his conclusions. Leibniz's calculus accepts the use and validity of infinitesimals at the outset, and began the notational development for infinitesimals in 1675 that is still in use today. Formal mathematical validity of using infinitesimals had to wait until 1963 for non-standard analysis by Abraham Robinson.
The mathematical physics description of reality, thus, became established with the development of calculus in the 1660s. Variational calculus, specifically, provides physical solutions and descriptions of reality that conform to observation, where the physical description of reality is in the form of a variational extremum. This is described in detail in classical mechanics, cm, and classical field theory, CFT. Having a variational process to select the optimum often devolves to solving some form of differential equation, reviewed in detail in the appendix. This is fine if you can solve the differential equation, but if you can't, it is beneficial to have some other analysis methodology to select equations of motion. Thus, it was recognized very early on that you could have a selection process based on highly oscillatory integral constructions that self-select for their stationary phase component. This latter path will eventually lay the foundation for the path integral approach to quantum physics, see reference 42, and to all of the classical physics that came before as a special case. Introduction of mathematical physics concepts before formal mathematical validation is a recurring theme in physics. Another such instance is the introduction of the delta function by Dirac, formalized via L2 distribution theory. This is what is critically needed in the underlying, self-adjoint, quantum formulation.
2.1 Newton's force law and, with Leibniz, invention of calculus. Let's begin with a restatement of Newton's three laws. First law, the derivative of p with respect to time equals 0 if f equals 0, where p equals mv and m is mass, and v is velocity. Second law, the derivative of p with respect to time equals f gives f equals ma. Third law, the force exerted between two objects is equal and opposite. Equation 2-1. And, when there is more than one particle, we have for the equation of motion for the ith particle the sum from j to a vector f sub j I plus vector f sub I equals vector p sub I. Equation 2-2. Where vector f sub j I is the force of the jth particle on the ith particle, vector f sub I equals 0. Vector f sub I is the net external force on the ith particle, and vector p sub I is the time derivative of the momentum of the ith particle. Recall Newton's third law, where the force exerted between two objects is equal and opposite, i.e. vector f sub j I equals negative vector f sub ij. This is referred to as the weak law of action and reaction.
In Chapter 1 Problem 6, page 31, of Goldstein, outlined below, we find that the standard equations of motion for the center of mass position and momentum, taken as starting point, not only indicates the weak law of action and reaction, but also the strong law, where the forces strictly lie along the line joining the objects. This convenient result occurs because the system equations of motion implicitly relate to system-level conservation laws, so, taken in reverse, we see global conservation laws constraining local dynamics and local force descriptions such that forces between objects strictly lie along the line joining the objects. This is developed more extensively in the context of Noether's theorem in a later section. For now, let's consider the center of mass system in detail, starting with the description of the center of mass coordinate that has equation of motion. See the next equation.
Where this relates to the equations of motion for the individual objects upon elimination of center of mass coordinate. See the equation shown. A direct comparison with the individual equation of motion above, when it's summed over objects, shows that we must have. See equation 2-3. Thus, we obtain the weak law of action and reaction so far. Now let's turn our attention to the system description of angular motion, about the center, which relates to conservation of angular momentum. Starting with the system angular momentum and the change in angular momentum with external torque. See the next equation.
We first take the time derivative directly. See the equation shown. A direct comparison of the time derivatives of the angular momentum then indicates we must have. See equation 2-4. Again, let's focus on two objects interacting, labeled 1 and 2 vector r sub 1 times vector f sub 21 plus vector r sub 2 times vector f sub 12 equals 0, and since vector f sub ji equals negative vector f sub ij already, we must have vector r sub 1 minus vector r sub 2 times vector f sub 12 equals 0, completing the strong law of action-reaction proof. The forces strictly lie along the line joining the objects, allowing a potential function description in later analysis.